This video is part of a series in which we step through the design of an 8-bit microcontroller core in System Verilog. In this video, we'll give an overview of the Arithmetic Logic Unit. Since this is an 8-bit computer, the ALU will take 8-bit inputs. These will come from the A and B registers, and the output will go into the A register, but the ALU is purely combinational. There's also a carry in output, and the condition codes are set on the output. The function code determines which of the operations the ALU performs, and the encoding is exactly the same 4 bits that appear in the opcode of the ALU instructions. So now let's take a look at the Verilog code for the ALU module. Before we do that, we define some symbolic names for all of the 4-bit function codes, and these values exactly match what we will find in the function field in the ALU instructions. So here is the ALU module with its inputs and outputs, and we see the A and B and the carry going in along with the function code. The outputs are prefaced with this O underscore, and here we define some logic elements with the exact same names, and all we're doing is assigning as the output of this module the value of these logics. We need to use logics because we have an always comb construct, and that requires the logic elements. The next thing we do is we define some values for the result of the addition and the result of the subtraction. We also define the result of the overflow computation for the addition and the subtraction. Notice that these are 9 bits and not 8 bits. So here we compute the result of the addition. These are 8-bit values, but they will be extended to 9 bits, and we will use the 9th bit of the result as the carry output. And we add in a carry input if this is an add with carry operation. So we test the function code, and we either use the carry input or just 0 in the addition. And we do the same thing with the subtraction down here. We subtract A minus B. And for the borrow, if it is a subtract with borrow operation, then we use the carry input. Otherwise, we use 0. Here we compute the overflow. And basically, we're looking at the sign bits of the A and B input and the sign bit of the computed result. And we're asking if, in this first line here, if A and B are both positive, is the result also positive? If it's a negative, then that would be an overflow situation. Likewise, if A and B are both negative, then the result had better also be negative. If it's a positive, then we would set the overflow. Subtraction is almost the same test. We look at the signs of the A and B inputs and the sign of the computed result. And we have these two possible cases. In the case of a subtraction, we can think of it as adding a positive number, okay? But we negate that, so it's adding a negative. So adding a positive and subtracting a negative is the same as adding a positive with a positive, and so the result had better also be a positive. And then the last test is similar. When we have a negative and we're subtracting a positive, it's the same as adding another negative, and the result had better be negative. So once we've got these set, we can look at the always comb. Now I'm using the Icarus simulator, and it objects to the always comb construct, so I'm using this older form in place of that, but you probably want to code always comb if you're using System Verilog. So here are the values that we're going to be setting in this, and notice that the condition codes will be 0 by default. If they're not otherwise changed, the output will be zeros. And in each of the cases, we will set the ALU output. So I suppose I don't have to do it here, but maybe it's good practice. So this is just a gigantic case statement, or a switch statement if you will, on the 4-bit function code. So I do each of the possible function codes here, and, or, and so on. And then down at the end of this case statement, we always set the sign output and the 0 output. We look at the result and we look at the most significant bit. That will be the sign condition code output. And we also test the result to see whether it's all zeros, and if so, we output a 1 for the 0 condition. The others, the carry output and the overflow output, are set individually based on the different functions. So you can see when we take care of the AND, OR, exclusive OR, and NOT, we just perform the computation and we leave the carry output at 0 and we leave the overflow output at 0. So it will set these flags for those operations, but they will be set to 0. Here we see the addition and the add with carry, and in both cases we just use the result that we've computed before, that is the 8 bits of it, and the carry is picked up from the 9th bit, and the overflow is what we computed earlier. And that's how we do the add and add with carry, and the subtract and subtract with carry uses the same sort of idea. And then we have the increment and the decrement. These do not set the carry or the overflow bits. Here we have the clear, and I have a blank line which I need to eliminate. And then here we have the arithmetic negation. So we take the way to negate a signed value, as you may recall, is to logically flip all of the bits and then add a 1. And so that's exactly what we're doing here. We do set the overflow output. There's only one case in which the negation can overflow, and that's in the case of the most negative signed number, in which case we set the overflow to 1, and otherwise we keep it at 0. And then we have the shift operations. We have 2 left shift operations, and in both of these what we're doing is we're taking the input, the 7 least significant bits, and we're moving them over and concatenating them with a 0 in the case of shift left, or with the carry input in the case of the shift left with carry. And then our carry output will be what was the most significant bit of the input. And with the shift right, we have the same thing going on. We have our 6 bits moved over to the right, and we move a 0 in on the left end. Or in the case of the shift right with carry, we move the carry input into the most significant bit. And the carry out then becomes what was the least significant bit of the A input. And then I have a default here, although I think I've covered all of the cases. And that's it for the ALU module. It's critical that we test our ALU module before we proceed, because if there are any bugs, then they will manifest themselves later, and it will be just a nightmare to try to figure out what's going on and chase those down. So I've got a test bench for the ALU, and it's a lot of detail here, but I'll just walk through quickly the main ideas. So here you see the ALU, and we are instantiating it right here with registers for the inputs. So here we have some registers for the inputs and wires for the outputs. And then I do the initial begin, display a message, and then I run through a bunch of tests. So with each test, I'm using a task. The name of the task is do test, and I'm providing a bunch of inputs that will stimulate the ALU module, and I am providing some outputs that are expected from the ALU. And it took me quite a while to set up all of this test data. There's really quite a bit of it, particularly for the addition and subtraction with the overflow and the carry inputs and so on. And I've worked through a lot of these test values. And after running this test bench, I feel fairly confident that the ALU is working properly. This do test task is pretty straightforward. I am using the inputs here that I invoke it with, and I'm setting up some strings to make my printed output look nice. And for each test, that is each time this task is used, it will print a single line, and it uses some strings in order to print the test in some human readable ways. I'm also wanting to print the input values and the output values both as unsigned numbers and signed numbers. So for that I use a signed register, and I copy the input values. Here we're copying the input values to the signed registers, and then I can display both the A and B registers as well as the A and B signed in decimal. Register will normally display as an unsigned value, but if it has a signed prefix, it will. You'll see the plus or minus sign. And then I stimulate the ALU, wait 1 clock cycle, and then clock in the output and display all of the output. And the display is pretty complex, but basically I'm just displaying one line that shows the inputs, the outputs that it produced, and then I'm printing the information in decimal. And that's useful if it's an addition or subtraction, and doesn't hurt anything if it's not. And then I check to make sure that the actual output from the ALU matches the desired output that was provided to this task. And if there is any problem with any of the output, then I display a line along with the desired output values. And that's it for the test bench for the ALU module. Now once we've got the ALU module working, we can go on to the next module, and for that I will see you in the next video.